Therefore, without further ado, I will welcome Prof. Haniza for sharing her presentation.
Okay, Assalamualaikum warahmatullahi ta'ala wabarakatuh. Thank you very much, Aisha, our MC for today. So first of all, I would like to thank Dr. Tini from Inspem UPM and also Dr. Roslan from UMT. It's a good venue for all of us to be together today as a seminar. I was told that your seminar is conducted like every week or month, Dr. Tini?
Every week, but depend on presenter.
All right, okay. Welcome everyone that are joining us. I can see so many familiar names, some faces, profile picture from so many countries. Good afternoon from Malaysia, good morning. We have from Nigeria, from Saudi and others. Dr. Munira from the northernmost part of Peninsular Malaysia. Okay, let me share my screen. Okay, I hope everyone can see my screen. Yeah, Aisha?
Yes, Prof, we can see your slide.
All right, okay. So today I would like to share about graphs associated to groups. Okay, and in this seminar of algebraic structures and graph theory. So with us today, I assume that so many graph theorists in Malaysia. Dr. Roslan is one of the famous graph theorists in Malaysia. Right, I'm from, as mentioned by Asha, Department of Mathematical Sciences, Faculty of Science. I don't think this is the right slide, but let me try and see. Wait, yeah. All right, okay. I changed so many times until I shared the wrong one, sorry. Give me 2 more minutes.
Oh, okay, Prof, no problem.
Let me see. Yeah, this is the right one. Okay, sorry about that. Okay. Right, share again. Yeah. Sorry, there's a typo in my... All right. Okay, so can see it now, right?
Okay.
Okay. Can you see the second page? Okay.
Yes.
All right. So that is my email. After this, we should get connected. If you need to send me any email, discussion on research, this is my email. It's my initial at utm.my.
Sorry, Prof, can you make it full screen?
Full screen?
Yes.
Okay, view full screen mode. Wait. Is it now?
Wait for a while.
It's not okay, Prof.
It's
not
black.
Okay, not appearing anything.
Yeah.
Oh.
Yes.
Okay. Black. Because I can see my full screen now with me. Let me try again. Stop presenting. No, I'm not used to Meet. Normally I use Zoom. A window. Let me try again sharing this. What do you see? Do you see my slide?
Yes, the full screen slide.
You see it now?
Yeah.
Okay.
Yes.
You see the applied algebra and analysis group?
Yes,
Yes,
Doctor.
yes.
Yes, Prof.
Yes, Professor, you can see your screen.
Okay,
Hello
I
from
just see
Thailand.
the screen. I don't see any face at all, so I just look at the camera. Okay, you mentioned about my department, right? But I'm also belong to a research group. In the faculty, we have Applied Algebra and Analysis group. This is under the Frontier Material Research Alliance. So all are welcome also to like our page. This is our page, okay? And you also have seminar every week. Our seminar is not every week, but we do have some activities. So I hope that we can get connected. We can collaborate together, our students and researchers after this, okay? And our research area is more to the algebra. We have group theory, also in graph theory, formal language theory, spacing system, also in analysis, because it's applied algebra and analysis group. So among activities that we have, workshops. So if we open the workshop to others, you wait for the announcement in our Facebook page. Okay. I hope this has moved to the next slide. Is it?
Yes, Prof.
All right. Okay. So today I want to share on some pictures on graphs associated to groups. Okay. These are the work by my PhD student, Nabila Fikria, Nur Hidayah, Atira Farhana, Nabila, Amira Fadina, Atira, and Dr. Nur Idayu. I think most of them are here, if not all. And the topic will be all related to graph and some of the properties, and also what can you do after you get the graph. Okay, the first one would be the non-normal subgroup graph of some finite groups. The second one is zero divisor graph of non-commutative ring. The third one is non-zero divisor graph of a ring, graph polynomials, energy of graph of groups, PI Kelly graph of some groups, and the last one would be on topological indices of non-commuting graph of dihedral groups. I have shared this slide with Aisha earlier. So when you fill out your registration form and put in your right email, later Aisha will email to you, right Aisha?
Yes, correct, Prof.
Excuse me, Professor?
Yeah.
Where can I see the registration form?
From the chat box.
It's in the chat box, you see?
Okay.
Maybe you can put it again for those who just join us. Okay, so the first one.
Okay, thank you.
All right. The first one is on the non-normal subgroup graph of some finite groups. Okay. When you see the bracket 1, that is actually the reference. So this work has been published by Nabila and the other authors, and later on you can get the papers, published papers in my website. Actually, I uploaded the papers in my website, okay? You can get my website. Later, I will share the link. Okay, so what is a non-normal subgroup graph? Okay, what is actually graph associated to groups? Okay, everyone here, I think, I'm sure is very familiar with graph in graph theory, in which a graph has a set of vertices, right? And edges. So you have some vertices in a set and also edges connecting some of the vertices. So when you associate graph with groups, you use the property that you have in groups to put in or to define this graph, the vertices of the graph and also the edges using the properties in the groups. So you will see the differences in the vertices of all these graphs that I will be sharing this afternoon or morning in Nigeria. Okay, the first one is called the non-normal subgroup graph. So we need to have group, because we associate this with group, we need to have a set of vertices and also edges, and this is how we define. So let G be a group and H a non-normal subgroup of this group G. I assume everyone knows group, right? It's a set, it's a closed, associative, identity, and inverse. So every group has at least one subgroup. It can be trivial, it can be the whole group, or it can be non-trivial proper. And we have also normal subgroups and non-normal subgroups. So you pick all the non-normal subgroups, we call it, that's why we call the graph non-normal subgroup graph. So the non-normal subgroup graph, gamma, we put N and G, is a directed graph with vertex set G such that X is the initial vertex and Y is the terminal vertex. So the vertex set is the whole elements of G. Then we have X and Y connected if they are not equal, and the product or the X times Y is in that subgroup H. So you pick any two elements and you check whether the product is in H or not. Okay. For sure, if X and Y is in H, then the product is in H, right? Because H is a subgroup. Okay, that is the trivial one. Now, I give you one example. We have so many different kind of groups, but today I will just choose the generalized quaternion group of order 12, right? Q12. You remember you learned about quaternion group of order 8 normally, right? The plus or minus I, J, K, in which you have a plus or minus 1. So this is bigger than that. You have order 12, and you have to figure out to find the non-normal subgroup of G. So the elements of this Q12 is generated by A and B. All right, this is a quaternion group generated by A and B. So you have all this. So you see here, A has order 6, right? And B has order 2, right? So we have all this product of A's and B's becomes the elements of G, becomes the vertex of the graph. And then you have the non-normal subgroups of this. We have 3 of them. So we have to find the non-normal subgroup graph depending on the non-normal subgroup. So when H is this subgroup of order 4, we get the graph to be gamma H1 of Q12 union with the complete graph of order 4. You see, for each of these non-normal subgroup of this graph, it's always this graph here. Next page is the graph union with K4, and actually they all have the same shape. Okay, the changes are just the vertices. This is quite interesting. You see, the graph is this union with K4, right? Then you can make it actually bigger. Now, for the next one, I want to also share this example because this gives a little bit different of the graph, right? You have quaternion group of order 16. So you have A of order 8 and B of order 2. So these are all elements of the quaternion group of order 16. And the non-normal subgroup graph, we have 4 non-normal subgroup of G. And the non-normal subgroup graph turned out to be this part, union with 2 of complete graph of order 4. Okay. And this part, they all look the same, but difference in the vertices. So there is an idea of getting the general form of this whole thing. So this is what we have been doing, right? So this is the non-normal subgroup graph. The second type of graph related or associated to groups, we call it zero divisor graph of non-commutative ring. Okay, so I'm sure you still remember ring, it has to be a abelian group, but you have extra, right? Because ring, you have 2 types of operation, not only multiplication, but also addition. So we let R to be the non-commutative ring. Although it's a abelian group, it's commute under the addition, but we don't want it to commute under multiplication. So choose R to be non-commutative ring. Then the zero divisor graph is defined to be a graph where the zero divisors are the vertices, right? The zero divisors, but we don't want to be the zero to be inside. They are the vertices, and two vertices are connected or adjacent if the product is zero, depending on the ring. The ring can be matrices and others. And how do you define zero divisors? I'm sure you still remember. X and Y are called zero divisors if X and Y are not zero, but the product is zero. All right, like Z12, right? Z12. 3 times 4 is 0 because it's modulo 12. 3 is not 0, 4 is not 0. 3 times 4 is 12, which is 0 in Z12. So there are zero divisors. So we try to find this zero divisor graph. I give you one example. Matrices, okay. R is 2 by 2 matrices in which the entries come from Z2, 0 and 1. So how many elements that we have in this set, in this ring? 2 here, 2 here, 2 here, and 2 here, right? So you have 2 to the 4, which is 16 elements in here. Then we can see that the zero divisor graph of this ring is a directed graph of 9 vertices, all the zero divisors, and 24 arcs at the edges, okay? Now, by the definition of zero divisor, we can actually find out from those 16 that we have this 9 non-zero divisors, right? 0, definitely we pull it out because 0 times anything is 0. We don't want it to be 0, right? So we want it non-zero. For example, when you multiply these two, so 0, 0 times 0, 0 is 0, 0, 0, and 0, right? So you multiply these two, you get 0 matrix. So they are zero divisors. So when you draw this in the graph, they are connected. And some of them are not. So we got to get this. So you see 1 and 9, they're not connected. 1 and 9. So if you multiply this with this, you will see with this 1, 0 here, you get 1, right? Oops. You get 1, 0 times here, also 1. So these two, they are not connected because when you multiply, they are not 0. So you get this. It's not complete because there are some of the vertices which are not connected. And we found that this with 9 vertices, and we have 24 with the edges. All right. The next one is commuting zero divisor graph, right? Commuting zero divisor graph. What's the difference? This one, we want to be xy is equal to yx equals 0, right? So in this case, we have only 6 edges for this one. Not only x times y is 0, y times x has always need to be also 0. So we call it commuting zero divisor graph. And for this one, right, you have to check 2 times 4, the vertices just now, and 4 and 2. So this one just to show and get you familiarized with this. And you can think to extend this problem to probably a general matrices or a bigger matrices to get this. Okay, the third graph that I want to share is on the non-zero divisor graph of a ring, right? Just now we see the zero divisor graph. What happened if we have a non-zero divisor graph? So this is the one that I was explaining before, that you have a zero divisor if the product is 0, right? And that is the zero divisor graph from before. Okay, there's some results containing click number and chromatic number. So I will just share again. I'm sure you still remember and very familiarized very familiar with this clique number of a graph, right? So a complete subset of a graph is called a clique. So you have this graph and you try to find the subset which is complete, right? All edges, all vertices are connected with edges. And the maximum size of this clique is called a clique number. All right. And the next one is chromatic number. So the chromatic number is defined to be the smallest number of color needed to color the vertices so that no two adjacent vertices share the same color, right? And this is the omega and the chi. All right. Diameter of a graph is the supremum of the degree from x to y when we have x and y vertices of the graph, right? And you know the number of edges connected to one vertex, they are the degree, right? The girth is the length of a shorter cycle in a graph, right? So just a review. Okay, now what is a non-zero divisor graph? The non-zero divisor graph, so find the vertex and then the edges, right? A simple undirected graph with vertices all non-zero elements. The vertices are all non-zero elements of a ring and such that two distinct elements are adjacent if and only if the product is not zero. Okay, you see some authors define the zero divisor graph as the vertices as the whole elements, the non-zero elements. Some define it as the zero divisors, non-zero zero divisors. And depending on the author, for this one, Atira Farhana did this for having vertices as non-zero elements of a ring. As an example, we look at Z6, right? 0, 1, 2, 3, 4, 5. Then the graph is an undirected graph with 5 vertices, right? 0, 1, 2, 3, 4, 5 minus 0. So 1, 2, 3, 4, 5 will be the vertices. And you can figure out the edges, right? You have 8 edges. Figure out how many the vertices that can be connected by multiplying, right? Like 2 and 3 is 0, right? 1 and 5 is not 0. So 1 and 5 are connected. So you can do this one by one. And from whatever you have from the graph, the clique and chromatic number turns out to be 4. Okay, so, but you have to find all the pair of elements and you will find out that there are 21 of them, right? And we don't have any loop. We don't allow to get x with x. So this is the non-zero divisor graph of Z6. Right now, you have like this, right? 1, 2, 3, 4, 5. So 1 and 5, like 1 times twice is 5, which is not 0, right? So the only vertices that are not connected, that are not adjacent, would be 2, 3, because 2 times 3 is actually 0. 3, 4, right? Because it's 12. So these are the only one. Okay. Okay. Next result shows for a commutative ring and the non-zero divisor graph of the ring for any commutative ring is a connected graph, and we can find that the diameter is at most 3. Okay. And depending on the cases, so the proof we have to divide into 4 cases. So we just take x and y distinct vertices in the graph. So the first case is when the identity is present in the ring. Okay. The second case is when the product is not 0. The third case is when the square is not 0. And the fourth case is xy is 0 for this one. Okay, so I'm not gonna go into the detail of the proof, but we don't want R to have the identity element. Okay, so for example, this is the non-zero divisor graph of Z12, the ideal of Z12, sorry. Right, so you can draw this, but there is a 6 and isolated vertex, right? There is no identity element in here, and this is not a connected graph, right? That's another one. Okay, we have this ideal of Z14. I'm sure you still remember the ideal in a ring, right? The set of ideals. Then this is a complete graph. So some examples, easy examples that we can see for this type of the non-zero divisor graph of cyclic group. Okay, now I will now introduce a center graph, and with this graph, we will look at graph polynomials, okay? And this one is focused only on the dihedral groups. Okay? To refresh your memory, if you remember dihedral groups consist of elements of rotation and reflection, right? Of an n-gon, right? So D to n, dihedral group, if we call it D to n, is of order 2n, right? Like D8, right? D8, depending, some authors use D4, some authors use D8 of order 8. So you have a square, right? 2n, n is a square, so you have rotation and reflection. Then you can have the 8 elements in the dihedral group. And this is not cyclic, so generated by, we call it A and B, right? Now again, we do some review under graph theory. We have independent set. So you have a graph. This is not necessarily graph associated to groups. Any graph, we have independent set of a graph. So we have a set of vertices that are not adjacent. They become independent set. Now from this, there's a definition of independence polynomial. Okay, this was defined in 1994. The author is Hodi. Okay. Independence polynomial of a graph is a polynomial containing coefficient that represent the number of independent set in the graph. So you have a graph, and then you can find the number of independent set, and this becomes the coefficient of the independence polynomial of this graph. And so many authors also study about clique polynomials, right? Just now we see what a clique is. So polynomial containing coefficient that represent the number of cliques in the graph. Okay, I mentioned about introducing the center graph. The center graph was introduced by Balakrishnan in 2011, this 10 years ago. A center graph of a group is a graph in which the vertices are all the elements of G. So elements of G becomes the vertices, and two distinct vertices are adjacent. If and only if this A and B, they are adjacent if A times B is in the center of this group G, right? You remember the center of a group is all elements in G in which AB is BA, right? For all elements, commute with all elements of G, right? That is the center. Like identity has to be in the center because identity commute with all other elements in the group G. Okay, so these are some properties we that we have in independence polynomial. Okay, if we have two vertex disjoint graph, right? Then the union, the independent polynomial of the union, x is the variables, right, in our polynomial. The independence polynomial in the union is the product of these two polynomial. Okay, this comes from the fact that the graph gamma 1 and gamma 2 are actually vertex disjoint graph. All right, so this can be used when you're looking for the union of the graph later, with the condition that they are vertex disjoint, right? The second property that we have is from this actually, right? You can make it general. The independence polynomial of the union of M, this one we don't need to be complete, right? But this one, the independence polynomial of the union of M complete graph, each of ni vertices, right? The union of the complete graph, the independence polynomial is the product of this polynomial, 1 plus nix, right? You see the ni is, this comes from the complete graph of ni vertices. They becomes the coefficient of this polynomial of degree 1. So it's a product of M polynomial of degree 1. This is quite nice actually. Instead of using the definition to find the independence polynomial of the union of the complete graph, we can just use this as the product of this polynomial of degree 1. The next is the independence polynomial of a complete bipartite graph of n1 plus n2 vertices, right? The independence polynomial of a complete bipartite graph of n1 plus n2 vertices is given as this formula. 1 plus x to the power of n1 for this one, right? Plus 1 plus x to the power of n2 from this one minus 1. Okay. Now, the center graph of this dihedral group, this was found in 2016. Let D2n be the dihedral group of order 2n, right? N is at least 3, natural number. The center graph, right? The center graph with the vertices of all the elements in which 2 vertices are adjacent if the product is in the center, right? That's the definition. So this is separated into 3 cases, okay, in which n is odd, n over 2 is even, and n over 2 is odd. Why do we need to separate this into 3 cases? Because for dihedral group of order 2n, this n, suppose n can be like 3, right? So the smallest one will be 3. So we get of order 6. If n is 4, right? If n is 4, when we divide by 2 is even. But if n is, say, even but 6, we divide over 2, it's odd. And there are differences in how we can prove this, in which we need to separate into 3. And the center graph of this dihedral group is the union of this complete graph and bipartite graph. All right. So this is n plus 1 union of K1 union with n minus 1 over 2 of the bipartite graph, right? When n is odd, this becomes even. And this is the union of K2, right? Since we get this is okay, so we get this number nicely, is even, right? And also this number is natural number. And the third one for the case n over 2 is odd, also is a union of complete with bipartite, right? And if you remember the property before, we can actually find the independence polynomial for this one, right? Using the property that is a union of complete graph. Okay, so again, while using the result of the center and the property that we have for independence polynomial for the complete graph, we also break up the result in 3 cases, okay? And this is found in Nabila Najmuddin's paper. This was in last year actually. Okay, D to N, which is the dihedral group of order 2n, and the independence polynomial of the center graph. We can find the independence polynomial of the center graph of many other groups. Okay, we can also find the independence polynomial in some of Nabila's work also for other kind of graph and for other kind of groups. And at the end, it's quite interesting to see how this independence polynomial or even the center graph differs from different groups, right? Or similar, although the groups are different. I remember in one of the SKSM, Dr. Roslan, you asked in one session, right? We know that if two groups are isomorphic, then the graphs have to be isomorphic, but the converse is not true, right? If two graphs are isomorphic, the group associated the graph with might not be isomorphic, but we can add some condition, necessary and sufficient condition to get the converse to be true, okay? Depending on also on the cases and on the graph. And for this one, this is how you see it. This is the independence polynomial. 1 plus x to a power times 1 plus 2x to this power, depending on the n, in which the n comes from the order of the dihedral group. The second one is, again, 1 plus 2x times the one with a higher degree, right? And we just have to be careful with the power, this one, because it depends on the n, right? This is still okay, n over 4 minus 1. And also the third one, right? You see these two very similar, but the index is different. Right? They differ in the index. And I mentioned about this earlier, but this is how you prove it, right? Using the lemma I show is 4.1 actually. That lemma before, that if you have a union of the complete graph, then you can compute the independence polynomial quite easily from multiplying the polynomials. Okay, this is for the second case when n over 2 is even and when n over 2 is odd, right? Just to match up the right graph with the right power of the graph and the union of how many? Complete graph. Okay, so this is directly from the proposition. Okay, for the next one is on the energy of graph of groups. Okay, from whatever graph that you have, not necessarily associated to groups, just any graph in graph theory, okay, we can find the energy of the graph, this group. And somehow this study on the energy comes also found from the chemistry part. The chemist is the name, hence the energy, and other applications on this that I won't share this afternoon, but I just mentioned this. Yeah, some applications. Always people ask, when you do this, what is the application, right? So at least we see some applications outside that used by not necessarily mathematician. They got the results, and the results can be found by us. Okay. Before I define the energy, okay, let's see what kind of graph that we have. Okay, so this definition is generating set of a group. In this study, we have some different kind of set of group. I did not say subgroup, I said set, right? So group is also a set. And before this, you see non-normal subgroup or normal subgroup. Now just find any set, and G is a finite group. So the elements of a subset S of a group G are called generators of G, and S is said to be a generating set if every element of G can be expressed as a finite product of generators. I'm sure you still remember in linear algebra, right? We study about vector space in which you have a generating set S that spans the whole vector space. So that is the generator set. Then we have a Cayley graph. I'm sure also that Cayley graph is very familiar to all of us. But this Cayley graph, we try to connect that with groups. Okay, so let G be a finite group with identity 1. X is a subset of G, of that group G. We don't want 1 to be in X, the identity, and X is equal to the inverse. Meaning, if you have an element X in X, X inverse has also to be in X, all right? Then the Cayley graph G on the subset X is defined as follows. Remember, if you have a graph, you have to have a vertex, you have to have the edges, the set of vertices and the set of edges. So the vertices are the elements of G, it's the whole G, and G and H are joined, or they are adjacent if, okay, G and H are adjacent if H somehow can be connected to G by X, meaning H can be written as a product of this X in X multiplied by G. Or you can write the other way around, X is H inverse G, or the other way around. But there has to have that X in X, so H and G are connected in this way, right? So the set of all Cayley graphs, we denote them as CAY, Cayley, G, with the subset X. So we need this X to define the Cayley graph. Okay, so in this research, we are trying to find the energy of a graph. For any graph G, for any graph gamma, the energy of the graph is defined as, so we use this epsilon of gamma, the sum of the absolute value of the eigenvalues. Okay, so we have to find the eigenvalues of what? Eigenvalues has to be from matrices, right? What type of matrices? So it's the sum of the absolute value of eigenvalues from the adjacency matrix of gamma. If you are not familiar with adjacency matrix, this is defined as a matrix, right, in which the column and the row are the vertices of the graph, right? Vertices of the graph, and the entry will be 1 or 0. If the vertices are connected, adjacent, then there is a 1. If not, they are 0. This is adjacency matrix. You remember from linear algebra that you find the eigenvalues, right, from the polynomial, characteristic polynomial, the summation lambda I minus A equals 0, and you get the eigenvalues. Okay, that is from linear algebra. Now, in our result, we choose the dihedral group of order 2n, right, and this subset of order 2. Okay, you can choose any bigger subset of any number, but we choose this as a subset of the general dihedral group of this. Then the Cayley graph, the cycle graph is the union of n over 2 C4. Okay, then with this one, spectrum is the set of eigenvalues. Okay, we have these eigenvalues: 0, there are n of them, and plus n minus 2 with multiplicity n over 2. So there are n over 2 plus or minus 2. All this as the eigenvalues. So how do you find the energy? Sum of the right? This one, the energy, you sum up the absolute value of those. All right, so you get the energy of the Kelly graph of D2N. So given a group, you have to find the Kelly graph. From the Kelly graph, you have to find the matrix. From the matrix, you find the eigenvalues. You take the absolute value, sum up, you get the energy, right? So this is a simple example of D8. D8 is a diagonal group of order 8, okay? So this is the generators and relation of this. So you have A of order 4, all the rotation, right? B, the reflection of order 2. So we have a subset of D8. We take just these two, A squared and B, right? Then we get the Kelly graph, the cycle of C4, okay? These two, union of C4, it's a cycle. And you can figure out the spectrum or the set of the eigenvalues to be 0. There will be 0, 0, 0, 0, you know, they are 8 by 8, right? 8 by 8, the matrix, because of the vertices. With multiplicity 4, and you also have plus or minus 2. Okay, this is the Kelly graph. Then, okay, so this is the, depending on the vertices, right? And the odd vertices, you put 0, right? That is for the adjacency matrix. You figure out finding the characteristic polynomial lambda I minus a, take the what do you call that? The determinant of that, right? What is it called? F lambda is lambda minus AI. No, it's not absolute value, but finding that out, determinant. Then you can figure out the this, okay? It's the answer is not just integers, but this is the set of the eigenvalues. Then you find the energy, which is the sum of the eigen, yeah, the sum of the eigen, the absolute value of the eigenvalues. Okay, I had to, okay, I still have like 15, 20 minutes. PI Kelly graph or some groups, okay? Just now we see Kelly graph. Now, what is actually the PI Kelly graph, right? So again, we have a group, and as a non-empty subset of G, I didn't say subgroup, it's a subset. Now let the order of G be the product of power of primes, okay? Any number is a product of power of primes. So you write the order of G to be P1 to the alpha 1 until Pk to the alpha k, okay? So we want this to be a finite number, right? Finite product of primes. Now, we define the subset, the non-empty subset, as based on that P sub I, okay? We have K of them, right? And this is the set of all X in G in which the order of X is that particular P of I to the power of N. To the power of N, and depending from 1 until the maximum of the power of P in here. Okay, and as before, as in the Kelly graph, S inverse is S. Okay, so we pick a special characteristic of this subset S, in which when we put P sub I here, we will choose the PI from 1 to K to be in this set. Now the PI Kelly graph, so the set of vertices, G is the set of vertices. So the vertices comes from this whole group G, and the same as Kelly, 2 vertices are adjacent if G H inverse in S, right? Before we write G is Hx, right? But this is another way to write G H inverse is in S for all G H in G. Okay, just to share some results. The 2 graph, when the prime, P is prime, is equal to 2 of the alternating group of order 12. If you want to recall, right, alternating groups comes from symmetric groups in which they all have even order, right? From S12, you pick all the even order. Then we have alternating group of order 12. Sorry, not S12, S4, right? S4. S4 has order 24. So we take half to be A4, right? So this is the symbol, is the regular graph in which each vertex has degree 3. Okay, it's a good exercise actually. The next one, the 3 graph. So when you replace 3 PIS 3 of the same group, okay, A4, we get the regular graph in which each vertex has degree 8. All right. Okay, now let's make it bigger. The direct product of the 2 graph and the 3 graph. So our group is the alternating group of order 12, A4. Okay, you take this direct product. We see before they are both regular. This is also regular with this many vertices. And this vertex has a degree 8. Okay, now it's not direct. The proof is not direct. You have to see the one before. You see 2 graph, it's regular, right? The 3 graph is also regular. And then you can find the number of elements in the direct product of both graphs, right? So you see how, and in the condition where the vertex, they are adjacent to each other. Then we use the definition of the direct product of graph, right? And we found them to be the regular graph. Okay. Okay, my last sharing for this afternoon, actually, I just share some graphs and some of the properties. There are papers in the references in my website if you are interested to see more, and there are lots more work are still going on for each and every one of these research. But this afternoon, I just want to share a little bit of each. So the last one would be topological indices of non-commuting graph for Dijkstras groups. Non-commuting graph is one of the very first graph associated to groups that have been introduced. Okay, and it's defined to be, this one has been, non-commuting graph has been defined by Ali Reza Abdullahi, right? In which year was it? 2006, yeah. So he defined non-commuting graph to be, okay, get a finite group, and the non-commuting graph is a graph with vertex set G without the center. You don't want the center to be in the vertex because you want them to be not commuting, right? If the center is inside, then it will commute with anyone else for the vertices. So take every vertices of G, take out the center, becomes the vertices, and 2 distinct vertices are joined by an edge when they don't commute. You also have commuting graph in which when they commute, then they are adjacent. Okay, for this research, we find the indices. So you can see there are many indices. And these also have very close relation with chemistry. Okay, they compute this so many indices. I will share some, I think 2 or 3 today. First is the Wheaton Index. Okay, this is defined by Wiener in 1947. Yeah, you have to have a connected graph. So this is number 1 condition. You have a connected graph. Doesn't matter what kind of graph can be related to groups, can be just any graph from graph theory with this vertex set, okay, from 1 to m. The Wiener index is defined as half of the sum of distances between every pair of vertices of gamma. So you will have a graph, you will have vertices, you will have the edges, and you take the sum of distances by every pair. You know, the distance is when it's connected, you count how many, right? And sum up all those, take half of those sum, and you get the Wiener index, right? Keep that in mind. Okay, next index is Zagreb index. Also, you have to have a connected graph. We have to have this vertex set. And the first Zagreb index is defined, there is a first, there should be a second, is defined as the sum of the square of the degree of each vertex, right? The degree is the number of edges connected to that particular vertex. And the second Zagreb index is the sum of the product of the degree of two vertices for each edge, right? So it's quite straightforward actually from the definition. If the graph is just simple, right? Not simple graph, but not too complicated. Okay, let's see one example here. Let gamma be a simple connected graph with these 4 vertices, 1, 2, 3, 4, and these edges, E1, E2, E3, E4, E5, right? This is not complete because 2 and 4, they are not connected, right? So to find the Wiener index, you have to calculate each distance, like from 1 to 2, from 1 to 3, from 1 to 4, 1 to 2, 1 to 3, 1 to 4. So 1 to 2 is 1, 1 to 3 is 1. Only 2 to 4, the distance is 2, right? 2 to 4, there is not adjacent here, there is no edge. So only from 2 to 4, the distance is 2. So the Wiener index is the sum of the distance of each of the vertex for the edge, right? So we have this 1, 2, 3, 4, 4 times, so we have 16. From the vertex to itself is 0. The distance is 0. The others we can see they're connected, the adjacent is 1 except for 1, right? So you can quickly see this, only 1 is 2, and the rest, only 1 is 2, right? 2, 3, 3, 2. What is it? 2, 4, and 4, 2, right? Only those 2. The rest, they're all either to itself is 0 and the others they are 1. So add up and take half. So this is the Wiener index. Okay. For the Zagreb index, you look at the degree. So look at the degree of each of those. The degree here is 3, 2, 3, and 2, right? So you put in the degree 3, 2, 3, and 2 and square and sum up. Okay, this is the first Zagreb index. For the second Zagreb index, you have to find those with the edge, right? Like there is an edge for 1 and 2, so you have to find this for this particular one, right? 3 and 2, right? 3 and 2, then the other one is 2 and 3 for each of the edges. And we get the second Zagreb index. Okay, some results that we found in general, right? I show you example in specific. So if you have a diagonal group D to N, then you separate into 2, then you get the Wiener index. Okay, so from the graph, you have to find what are the distance, right? The distance in general, then you figure out the Wiener index, you find the degree, and you find the Zagreb index. So just showing the results for the non-commuting graph of the diagonal group. This is the Wiener index. Depending on n, whether it's odd or even, you can just put in the number, then you will get a number, right? This is an integer. And for the first Zagreb index, we have this result, right? Then you can plug in the number, you get the number for the first Zagreb index and for the second Zagreb index, okay? This is by taking each of the edges. I didn't have time to show the detailed proof, but you can find this in our paper, right? This was published in 2018, right? Okay, so these are some of my references. The one that I mentioned earlier, you can see the last name of this student of mine. So you can see where you will get the details and how it is proved, like for number 1, for number 2, for number 3, 4, 5, 6, and 7. Yeah. Okay. Thank you very much again to Dr. Tini for the invitation, to Aisha, and to all of you who have given your full attention in this 1+ hour. I will put in aside probably some time for question and answer. And I mentioned about my website in which you can get some or most of the publication related papers from this, okay? And please fill out the registration form there in the chat so we get your email, and this slide can be emailed to everyone. If you want to send me an email, this is my email. Here we can also get connected in Facebook or LinkedIn. I would like to take this opportunity to thank Dr. Idayu for helping me to gather up all the slides and results, and also to my students who shared your results for today's sharing. Thank you.